Okie dokie. So we're on to 3.3, which is properties of logarithms. So we've addressed some of these properties already, but we're going to dig in even a little deeper. Some things that we know to be true about when we work with logarithms and those relationships. So the essential questions today, how can I use change of base formula to rewrite and evaluate logs? So we're going to talk about evaluating different logs. Use properties of logs to evaluate or rewrite expressions. So how can we use properties to help us? To expand or condense. So sometimes we want to kind of think about how can we pick these statements apart? Where do they come from? How do they go back together? Almost like a puzzle. And then how to use log functions to model and solve real life situations. So I'm going to give you a little historical note here. Who developed logarithms? So one of the key figures in this is John Napier. He was a Scottish mathematician. So if you have any Scottish roots, way to go about that. So it's really logarithms can be really, they say tedious, and it's absolutely true to calculate. And so being able to put them together and find some kind of shortcuts and properties and things are really a wonderful tool for us. So he worked on it for over 20 years on the development of his work on logarithms before he published it in 1614. So the mathematics you're doing today date back way back to the 1600s. So he only partially succeeded. Many people continued his work afterwards, but he was kind of one of the pioneers in that. So let's talk about change of base first of all. Depending on the kind of calculator you have, before we had calculators, we had log tables. We had these things we had to look up all these numbers in the back of a book, and I'm a dinosaur person, so I remember that. You have calculators that have log buttons on them, which is great, and you even have change of base on your graphing calculators, but not all graphing calculators do. Some of the earlier ones didn't. So we needed this change of base formula to be able to do that. Basically, get it? Basically, what you're looking at is writing it as an expression of either common logarithms or natural logarithms, or really any base that you want. So your base value, so if you look at log base a of x, a could be really anything. You can write this as common log of the argument, the number, divided by common log of the base. And the advantage to that, that ratio, so log base a of x can be common log of the argument, the x, over common log of the base. You have a base 10 key on your calculator. Also equivalent is natural log of the argument over natural log of the base. So you can rewrite any one of these formats. You can even change it to any other base that you wanted to. So log base b of the argument over log base b of your original base A. Now, I don't know why you'd want to change, say, a base 7 into a base 3, but you might want to convert over. So if that's the application you're doing, those ratios are always the same. So I have that kind of in a nice version here. So you can have it in base B, base 10, or base E, and it's always going to end up being the same. So for those of you with older versions of the calculator, that's what you would have to do. There is no other option. So let's talk about why this is so helpful for us. So log base 8 of 20. Let's remember what this means. Remember, logs are exponents. You're asking the question, 8 raised to what power would give you 20? Now let's make an estimate here first. What's 8 to the first power? Well, 8. What's 8 to the second power? Well, 64, so that's way too big. I want 20. So it's going to be somewhere between 1 and 2, probably closer to 1, right? Because 20 is probably closer to 8 than it is to 64, right? So it's a little bit closer, but it's going to be pretty close in between. So I know it's going to be somewhere between 1 and 2. It's not a whole number answer, though, so I can't just answer it by looking at it. So what we can do is we can rewrite it as using the change of base formula. So log of common log, log, of the argument, the 20, divided by log of the base, which is 8. Remember, the base always goes on the bottom, base and bottom. You could also do natural log of the argument 20 divided by natural log of the base, or 8. Okay, so here's what I'd like you to do. Pause the video, type both of those in separately, and see what you get. All right, super important to recognize, look at my bottom two things there, that they are identical answers. Notice I finished off the parenthesis after the 20. Really important. If you're using the fraction function and you're just going to do that, then you don't have to worry about that. So if you're using the fraction capability, which is alpha y equals, and you're going to do that, then great. Then you can just type it in, not a problem. But if you're using the divide symbol, which many people do, just don't forget you have to finish that off. That can be kind of an epic disaster if you don't. So just be careful. Make sure you're dividing the right thing. Now, some of you might realize that you do actually have a log base 8 of 20 function on your calculator. If I go back up to my, let's see, which one is it under here? There we go. Second one, it's alpha window. For me, that's log base, which is number 5. I can actually type in log base 8 of 20 and solve. Some calculators don't have that function though, and you need to understand that change of base does really help to convert into other things. But if you have the log base function, it can be really helpful as well. So you have that option on there. All right, let's talk about some properties of logarithms. So there's things that we can do to break apart and put back together logs. And if you remember that logs are exponents, it's the same properties as exponent properties. So I want you to think back to doing things with exponents. Like if you have an x squared times an x cubed. So if you're multiplying with the same base, what would you do with the powers? Well, x squared means x times x cubed is x times x times x. That would give you x to the 5th. What did you do with the powers? You added them, right? Okay, well, take a look at the first property, number 1. These are multiplied together. They're going to use u and v in the argument to stand for whatever those things are, variables, numbers, whatever, and the base is a. So when you multiply with the same base, what do you do with the powers? You add them. So this is log base a of v plus log base a of u first, I guess. Sorry, it doesn't really matter. And then v. So log base a of u plus log base a of v. So multiply goes with add. So we can go both directions. And we'll talk about this and we'll rewrite and make sure that this makes sense and that we can write out these properties and work with them. So we're going to be going back and forth. So multiplication goes with addition. Okay, so let's think about divide then. How would you do x to the 5th divided by x to the 2nd? Well, if you're dividing two things with the same base, what did you do with the exponent? You subtract, because that would be x cubed, right? If you have 5 of them and then you divide by x squared, we can divide out 2 and we'd be left with 3. So when you're dividing, you subtract. Okay, so we have dividing, we subtract the exponents. Well, the logs are the exponents. So log base a of u minus log base a of v. So dividing goes with subtract. Okay, now the last one I want you to remember is power to a power. So x cubed to the 5th. So that means x cubed times itself 5 times. I should have picked a smaller number. That's a lot. Okay, ooh, 3. So 3, 6, 9, 12, 15. Power to a power, you multiply, right? It's a product. So this is power to a power. U to the n is the same as n times the log base a of u. They're multiplied. Power to a power, you multiply the exponents. Remember, logs are exponents. So every time you write down log, you're saying a power. So what we want to be able to do is use this to help identify how to simplify things, how to solve them, how to put them together and take them apart, which we're going to do tons more in the rest of the chapter. But also today, just kind of focus on how do these properties work? How do we put together and take apart logarithms then? So here's just kind of a sneak peek at what we're heading towards here. How would you simplify then log base 5 of the cube root of 5 without using a calculator? So key thing here, many of what we're going to be doing are going to be without a calculator. I want you to understand the properties. So first thing to realize, radicals and exponentials do not play well together. So if we're dealing with logs and exponentials, anything written in radical form is kind of a disaster. So I would rewrite the cube root of 5 as 5 to a power. Remember what that power would be. It's 5 to the 1st. So that would be 5 to the 1 over 3. Remember, the root is always the denominator. So that's where I would start. Always write any radical thing as an exponent, because otherwise we're going to have some issues. All right, now, you might remember the property that we talked about for logs that addresses this. Log base 5 of 5 to the inverse is there. The bases are the same. They undo each other. If you don't, we can use this power property that we just talked about. 5 to the 1/3. Where else can that 1/3 go? Well, out front, it's the power property. So 1/3 times the log base 5 of 5. Now, why can we do this without a calculator? Well, what is the log base 5 of 5? So log base 5 of 5, let's set it equal to something. Rewrite it here as an exponential. 5 to the what would give you 5? Well, 1. So 1 times 1/3 would be 1/3. Okay, now we could go through the hassle of typing this into our graphing calculator. So I'm going to do I have my log, oopsie, I always keep doing the wrong one there. My log base here. So log base 5 of, oh, now we need cube root. So I'm going to go into math, cube root of 5. 0.333 repeating, that's our 1/3. It actually takes longer to type it in than it does to figure it out if you understand what the properties are doing. So lots of important things in this one. Radicals, rewrite as exponentials, and then make sure that we're using properties to help us simplify. All right, so our quest, our focus for today and then into day 2 is going to be working with more, instead of solving things, more rewriting things. So we're going to expand, and then we're going to be condensing. So we're going to be doing both. So we're going to start with expanding. Expanding a log expression means to rewrite it in forms that simplify the operations, properties that convert complicated forms into simpler sums, differences, and products. So those three properties that we talked about. So you're taking like something that's been put all together and breaking it apart into its smaller pieces. So expanding means to break it apart into the littler pieces. So think about like you have a puzzle that you put all the pieces together to make the picture. Now you're taking it apart to all the separate pieces. So something's been made and we're going to unmake it. So we're going to take those apart. So we're going to think opposite operations here. Like what are the operations that we would normally do and how would we undo them? All right, so the directions here are saying expand this natural log. And it would be the same if it was LOG base 7. It doesn't matter what the base is. This is a base E. We can still expand it. All right, I want you to think order of operations here for a second. So order of operations. What would you do first in this order of operations if you were going to evaluate this expression? Well, please excuse my dear Aunt Sally. My dear Aunt Sally. First thing I would do would be parentheses don't have any exponents. You'd start with y to the 4th, then you do multiply, divide. But in this case, you would times first, right? The x times that y to the 4th. And then the last thing you would do would be divide, because in a big fraction bar, it's kind of like a grouping. We do everything in the top, everything in the bottom. So that would be the order that we would probably do things. So we're going to expand, we're going to undo that. So we're going to undo kind of last thing first. So the last thing that we would do would be the divide. That's the first thing I'm going to undo. What is dividing two logs the same as? I'm going to go back to my properties here. That's property number 2. It's the difference of the numerator log and the denominator log. So this would be the natural log of x times y to the 4th minus natural log of 2. So the log of a quotient, that's a division, is equal to the difference of the logs. So make sure you realize that this is the log of the quotient is the difference of the logs. Now that was the division would have been the last thing we did. Now we're going to work backwards. The next to last thing we would have done was the multiply, right? Because we said we would have done the exponent first, and then the multiply in the numerator, and then the division. Okay, so we're working backwards now. So we did the divide, now we're going to deal with the multiply. So these are multiplied together. So that means I can separate them using the first property, property number 1, the log of the product, that u times v, is the sum of the two logs. So that means this would be natural log of x plus the natural log of y to the 4th, and then minus the natural log of 2. Nothing to do there, really. There's nothing to break apart. It's just a 2. All right, so I dealt with the multiplication. All right, now exponent. So I need to deal with my exponent. So I'm going to look at this 4th. That y to the 4th, where else can that be? That power to a power property. This is the last one, number 3. It can be up front as a product. So power to a power, you multiply. So this would be natural log of x plus 4 times the natural log of y minus the natural log of 2. And this is what we're talking about when we say expand into sums, differences, and products of just those individual pieces. So natural log of x plus 4 times the natural log of y minus the natural log of 2. Each one of the arguments is just a single thing. In the argument, there's no operations left to deal with. So no powers, no multiplying, no dividing. Everything is broken apart. That's what we mean by expand. All right, let's take a look at another one. It's very similar. We're just going to throw a radical in there so we can talk about what that means. And it's a log base 3. Totally fine. And it's expand again. All right, so talk me through order of operations. What would you do first? Well, you would do exponents. So that would be the squared and the square root, the radical. You would do multiply in that numerator. right? So we'd multiply the 4 times the x squared, and then the very last thing you would do would be the division. If you can think order of operations, it will really help you with undoing it and working backwards. So we're going to work backwards with the division first. So what is dividing two logs the same as? We'll go back to our properties. That's property number 2. It's the difference of the logs. So this would be log base 3 of the numerator. And if it helps you to think of that, that whole thing's a numerator, minus the log base 3 of the denominator, square root of y. All right, so we dealt with the division. It's a subtracting of the two logs. Multiplication, next order of business. So let's deal with the multiplication. So it's the 4 and the x squared. So the multiplication, the product of two logs, that's number 1, is the sum, or the log of the product, I should say, is the sum of those two logs. So this would be log base 3 of 4 plus the log base 3 of x squared, and then we still have our minus log base 3 of the square root of y. So I dealt with the multiply. Okay, now exponents. So the first one is pretty easy to deal with. So we have that x squared, that's that product power property, number 3. So that n comes out front. So that one makes sense, I think, to most people. Log base 3 of 4, though, there's no operation left in 4. We're good. Bring the 2 down. So that would be 2 times the log base 3 of x minus. Okay, now here's where we need to have a talk. Remember how we talked about that exponents and radicals don't play well together? So square root of y is not ever how I'd leave that radical. So I want you to rewrite that as a base raised to a power. So remember, square root is a root of 2, and it's y to the first. That would be y to the 1/2 power. So this is really log base 3 of y to the 1/2. So that's an exponent. We're still dealing with this exponent. We can bring it down front then. So it would be 1/2 times the log base 3 of y. And notice your arguments, 4, x, y. There's no multiplication or division or powers left in any of them. So remember, with radicals, we want to rewrite those as exponentials if we can. All right, so that's what expand means. All right, I'm going to have you take a peek at this one and see if you can give it a whirl. I want you to pause the video, think about order of operations, what would you do, and how do I work backwards to figure that out? So we're going to expand. Okay, so think about order of operations again. The last thing that you do, the divide, the first thing you'd probably do the 3x minus 5, right? That expression, so that difference there. And you'd be taking the exponent of it, so that radical. So you'd be doing the exponent, which is the 1/2 power. It's the radical, however you want to think of that expression, and then you would divide by 7. So you would do what's inside there, and then you divide by 7. So we're going to work backwards, and we're going to deal with the divide first. So the log of the quotient is the difference of the two logs. So it'd be the natural log of this radical minus the natural log of 7. Natural log of 7, there is nothing else to do with. It is just a single number. There's no operation there to deal with. Okay, remember how we dealt with radicals? That would be the ln of 3x minus 5 raised to the what? So square root is the same as the 1/2 power. So I'm going to go ahead and write it like that. We already dealt with the division, so we can deal with the exponent or the radical. Where else can the 1/2 power go? Out front. Product, power to a power there. So ln of 3x minus 5, and then minus the ln of 7. Okay, now here's something that you have to realize on the inside there. That 3x minus 5 is a binomial, and it's an expression. It's not just a simple multiplication or a simple division. There is no property to take apart things where the arguments are added or subtracted. 3x minus 5 is as far as you can go. There's nothing else I can do to break that apart. The only thing that we can do is the log of a product, a straight product, or a straight quotient. This is a difference. You are stuck. That's as far as you can go. So that's a single argument. So if you see adding and subtracting inside your argument, done. That's a single expression. It's a binomial. So that's what we mean by expand. All right, so for this day 1, we did expanding. For part 2, we'll get into the condensing, going the other direction.